you get sulfate ion. Okay, sulfuric acid found in car batteries, very strong electrolyte and strong acid because there's 2 protons that can leave. The next one. It loses its first hydrogen. It's defined as being a strong acid. But the second one is when it becomes weak. So it's not as strong with the second hydrogen as it is lost. You'll notice weak ones have what in the equation? Double arrow. So they're at equilibrium. The strong ones are almost 100% forward reactions. Triprotic acids, like phosphoric acid. The first proton that leaves actually is a weak electrolyte and weak acid. The second one that leaves is also a weak electrolyte and weak acid. And the third one that leaves is also a weak electrolyte and weak acid. But there's 3 protons that can be put into the solution. So this can change the concentration of the hydronium ion in the solution, even though each process is a weak acid. So monoprotic, 1-step, diprotic, 2-step, triprotic, 3-step. Yes?
Okay, so the acetic acid, so it has more than 1 hydrogen atom.
That's correct. This is the only one that's ionizable.
Oh.
So the other ones are drawn together. This is often referred to as an organic acid because the molecular structure of it is that you've got CH3 here, and then you've got COOH. And because of the molecular structure, these H's here are not ionizable, but this one here at the end is ionizable here, just based on its molecular structure, which we will get into later. Now, a neutralization reaction is where you have an acid and a base forming a salt and water. The cool thing about this is it is called a neutralization reaction. But if you think about Santa Claus, it's just a double replacement. Yes, sir? Oh, I'm sorry. C, did I write the wrong molecule? I added an extra C, didn't I? CH3C. Oh, pardon me. Sorry. I do need to get something to eat. We go COOH. Pardon me. That is the molecular structure. Yeah, I was trying to invent my own molecule. Pardon me. That's acetic acid. The acetate ion is this here, and that's the hydrogen of the acetic acid. Thank you for checking me on that. Neutralization reactions here. You have the acid and the base added together to make the salt and water. If you think of the water as HOH, this is just a double replacement reaction. Just like the precipitation reactions you were doing today and yesterday. So if you think of it this way, H plus Cl, Na plus OH. The H and OH come together to make HOH. HOH is often written as H2O. So if you write it as HOH initially, you'll see that it's a double replacement. They swap partners. NaCl, HOH, making water. The Cl's cancel out. The NA's cancel out. You're left with H plus OH making H2O. Looking at just the water being formed. Yes. I can go backwards, I can go forwards, but I cannot go sideways in a PowerPoint. Yeah.
So does that mean that bases usually have hydroxides in them?
Usually. But ammonia does not. But they usually have hydroxides, but they always accept protons based on the Bronsted-Lowry definition. The definition of having a hydroxide in it is called the Arrhenius definition. Starcraft, your base is under a salt. It's a pretty creative one. Very, very good. All right. Strong and weak acids. Don't get it. Your base is under a salt. That's a salt, that's a base. All right, got it now? No. All right, strong acids. They dissociate completely. Weak acids dissociate less than 100%. Strong and weak. Strong, 100%, weak, everything else. Dissociation is the key to strong and weak for acids. A strong acid, 100% dissociate into H and A. Weak acid, HB. Some gets H, some gets B, the rest is still stuck together. It's all about dissociation. Strong, 100% dissociation. Weak, not so much. The scary 6. This we need to stay on and not go back. You need to know these strong acids when in water. Please write this down. If they're not scary now, they will be if you don't remember them. Each of these, of the scary 6, 100% dissociation in water. They're all strong acids. Because of the 100% dissociation in water, now all you need to know is the actual formula of this, and you know if they dissociate, it dissociates into hydrogen and the anion. Six. And then number 7, your HSO4. Yep. Now, the rule on when you are making an acid, you use your M1V1 equals M2V2 equation, or MI/VI equals MF/VF. You always add the acid to the water. The rule is do as you oughta, pour acid into water. If you do not, if you add water into acid, what can happen is the water will explode up into your face with the acid. Yep. It's in alphabetical order if you ever forget. Acid to the water. Now, strong acid. Johnny was a chemist's son, but Johnny was no more. What Johnny thought was H2O was H2SO4. Bases. They react completely with water to give OH ions. Sodium hydroxide. Strong bases. Weak bases react only slightly with water to give OH ions. Ammonia is weak. NaOH, strong. NH3, weak. We got to know what strong and weak are by now. Dissociate completely, don't dissociate completely. The pH scale shows a comparison of acidity and alkalinity, which is also another word for basicity. Normal range of precipitation, pH, usually between 5 and 6. 7 is neutral, That's where water is. Baking soda, seawater, and lye. Ammonia is up here. Lye is also another word for sodium hydroxide. Battery acid here, lemon juice, and vinegar, which is acetic acid. Yes, sir?
Isn't there stronger acids with like negative?
Absolutely. Yep, you can go past 0, you can go past 14. This is just a scale. Now, the pH scale here. Strong acids tend to be in this range. Weak acids tend to be more towards 7. And then as you go up, again, you decrease the concentration of the hydrogen ions. pH scale is all based on the power of the hydrogen ion. That's why it's called the pH scale. When you use a titration, this is a solution of accurately known concentration is added gradually to another solution of an unknown concentration until the chemical reaction between the two solutions is complete. When the reaction is complete, it's called the equivalence point. That is the point at which the reaction is complete. Indicator is a substance, like the cabbage juice, that changes color at or near the equivalence point. There are many, many different indicators that can be used, and you usually want an indicator that changes at the equivalence point for a good indication. The equipment that's used in a titration, you slowly add the base to the unknown acid until the indicator changes color. If you look up here, you see the solution is what color here? Clear. What color here? Okay, very, very light pink. That is the indicator point for this particular indicator, which is called phenolphthalein. Key titration terms for our titration lab. Titrant. That is the solution of known concentration used in the titration. So if you have a known base, that's your titrant. The acid is your unknown. Analate. That is the substance being analyzed. If it's hydrochloric acid, which is unknown, that's your analate. Equivalence point. Enough titration added to react exactly with the analate. Stoichiometric mixture is created. The exact endpoint is called the equivalence point. Endpoint, point in titration when the indicator stops changing color so you can tell when to stop adding the titrant. It's often the equivalence point for most reactions. So we're going to add the titrant to the analate to make it get to its endpoint. At that point, we should have the equivalence point with the exact stoichiometric ratios.
Question on this.
Yep.
Wouldn't the endpoint be the equivalence point? Is it always like the
It usually is. But that's assuming we have what's called a strong acid, strong base titration, which we will start with. But it's not always. That's why there's two different words describing it. Not always. But we are going to start with the case where it is. Now, for a successful titration, the reaction between the titrant and analate must be known, the reaction must be rapid, and the amount of titrant and analate must be known accurately. The endpoint must occur as close to the actual equivalence point as possible. You can have the wrong indicator and you'll get an endpoint that's way off the equivalence point. That's not a good titration. The equivalence point is a test of patience. When you titrate an acid with a base using phenolphthalein, you add it slowly and swirl it. If you get too purple, you've gone too far. You've gone past the equivalence point, past the end point. You want it to get light pink. Use a white piece of paper underneath it. In titrations, you have to stop at exactly the right moment. If you go too far, titrations can be used in the analysis of acid-base reactions, redox reactions. We will be doing both of these titrations. Come on, redox. And you'll see color changing depending on the reaction you are performing. So acid-base first, redox second. In titrations, another definition of this is you will experience frustration, no matter how much of a perfectionist you are. Now, performing calculations for acid-base, you want to list the initial species and predict the reaction. Write the balanced net ionic equation, calculate the moles of the reactant, and determining the limiting reactant for an acid-base reaction. You want to calculate the moles of required reactant / product, depending on where you're trying to get to, and convert grams or volume as required for this particular acid-base reaction. So an example of this would be what volume of this solution is required to titrate 25 milliliters of 4.5 molar sulfuric acid solution. So the first step is to write the chemical equation. The acid and base are making water and a salt. Make sure it's balanced. Then you look at the volume of the acid. Use molarity of the acid to get moles of the acid. You use the reaction coefficient to get moles of the base. That will tell you, converting using the molarity of the base to get to the volume of the base that is needed. So 25 milliliters, molarity of the acid gives us moles of acid. That gives us moles of base. And the last one gives us molarity to get the volume of the base, which happens to be 158 milliliters in this case. Units cancel out, of course. Come on, there we go. Giving us our milliliters needed for this particular titration. The titration equation looks exactly like the dilution equation. M1V1 equals M2V2, or MAVA equals M2VT if you like letters. So MA is the analate, MT is the titrant. This only works when it's a 1-to-1 ratio. If it's not a 1-to-1 ratio, you can still use it, but you have to use some ratios in it. You would have to use ratios of the M's. So you have to have molarity ratios built into it. So, second example using MV, our MV equation. It's known as the molarity volume relationship. If you set it up like this, unfortunately you're in bad shape because it's not a what? Not a 1-to-1 ratio. So you can put a 2 here. Look at that. Put a 2 here in front of the sulfuric acid. So it totally will work out. So, midterm study guide, you should be working on that, and 182. Good luck. We'll see you tomorrow.